This is Gauss's law, the second video in the Introduction to Electricity and Magnetism series. In this video, I'll explain Gauss's laws for electricity and magnetism. We'll begin with the point charge paradox. Then, I'll use the formula for the electric field of a charge distribution to derive Gauss's law for electricity. After I explain Gauss's law for magnetism, I'll apply Gauss's law for electricity to find the electric field of a uniformly charged plane. Recall from the first video that the electric field of a point charge Q is Keq over r squared r hat. We'd now like to compute the divergence of this field, how much electric field is being created at each point. First, let's review spherical coordinates and get a formula for the divergence in spherical coordinates. We use phi, theta, and r to define a vector in space. Phi is the angle between the positive z-axis and our vector. Theta is the angle between the positive x-axis and the projection of our vector onto the xy plane. Finally, r is the length of our vector. When we have a vector function, such as the electric field E, written in spherical coordinates, the output of the vector is also in spherical coordinates, so we write it as Vr, v theta, v phi. In this form, the divergence of V is 1 over r squared partial r of r squared Vr plus 1 over r sine theta partial theta of sine theta v theta plus 1 over r sine theta partial v phi partial phi. With this formula in hand, we can go back and figure out that divergence of E. Expanding the divergence of 1 over r squared times r hat, you'll notice that all the derivatives are applied to constants, so the divergence vanishes. Keep this in mind during the next calculation I do. Given a sphere S around our point charge Q, I want to compute the surface integral over this sphere of E. This requires choosing an orientation of the sphere, so let's make dA point outward. I can rewrite the integral in spherical coordinates and pull out the constants ke and q. Then r hat dot r hat and 1 over r squared times r squared are both just 1, so the integral gets a lot simpler. The integral from 0 to pi of sine theta is negative cosine of pi minus negative cosine of 0, which is 2. And of course, the integral from 0 to 2 pi of 2 is 4 pi, so the whole surface integral comes out to 4 pi keq. You might notice that the result doesn't depend on the radius of the sphere I used. It'll be true no matter how tiny a sphere we take around the charge. Now, let's go back and compute the same integral using the divergence theorem. The integral of E over the surface of S is the same as the integral of the divergence of E over the ball enclosed by S. But, as we just calculated, the divergence of E is 0. Therefore, the whole integral is 0. This is what I call the point charge paradox. 0 is not equal to 4 pi keq. It's worth thinking a bit about where we went wrong in our calculation. When I simplified 1 over r squared times 0 to just 0, that made sense everywhere except r equals 0. But at the origin, where r is equal 0, we're dividing by 0. In fact, E isn't even continuous at the origin, so it makes sense that we won't be able to find a function that's equal to its divergence there. What we can do is figure out how to integrate expressions containing the divergence of 1 over r squared r hat. If my integrand is f of r times the divergence of 1 over r squared r hat dv, the output is 4 pi times f of 0. Delta cubed is some notation we use in this sort of situation when taking an integral of f really just involves evaluating f at a point. Technically, delta cubed of r minus r prime dv is a measure with respect to which we calculate the integral, and that measure is a point mass at r prime. Now that we've got that cleared up, we can compute the electric field of an arbitrary stationary charge distribution and use that to derive Gauss's law for electricity. We're going to need two systems of coordinates, the primed coordinates to integrate over the charge distribution, and the unprimed coordinates to point to a location in space. The value of E at r is ke times the integral of r minus r prime divided by the length of r minus r prime cubed times rho of r prime dv prime. This formula comes right out of integrating over a distributed charge, our formula for the field induced by a point charge. Don't be confused by that r minus r prime over r minus r prime cubed. That's exactly equal to the unit vector of r minus r prime over r minus r prime squared, 1 over r squared times r hat, except that I've rewritten it without referring to the unit vector. Rho is the charge density, so units on rho are coulombs per meter cubed. With this general formula for E in hand, we can go ahead and compute the divergence of E. Using Leibniz's rule, we can pull the divergence inside the integral expression. Then we know the divergence of r minus r prime over the length of r minus r prime cubed, at least when under an integral sign, is 4 pi delta cubed of r minus r prime. So the whole integral just comes out to 4 pi ke times rho evaluated at r. This is Gauss's law for electricity. The divergence of E is 4 pi ke times rho of r. Now's a good time for a sanity check. The units of the divergence of E are newtons per coulomb meter. Ke has units of newtons times meters squared over coulombs squared, and rho has coulombs over meters cubed, so you can check that everything works out. Next, I'll explain Gauss's law for magnetism. The divergence of the magnetic field, B, is 0. I promised in the first video that I would explain how B arises, and Gauss's law for magnetism says a little bit about how B doesn't arise. Magnetic field is never created at a point in space, and the amount flowing into a region is always the same as the amount flowing out. On the right, I have the magnetic field induced by a wire carrying a current, and on the left is the impossible field of an isolated North Pole. Gauss's law for magnetism is an experimental fact. I could derive it for classical magnetism, but the real reason we have it is that physicists haven't found any magnetic point charges in the real world. Gauss's law for electricity, on the other hand, has lots of applications, and I'd like to show you one striking example of how powerful a tool it is. First, I need to derive an integral version of the law. Using the divergence theorem, we get that the integral over a closed surface S of E is equal to 4 pi ke times the charge enclosed in that surface. Okay, so here's the problem I want to solve. Can we find the electric field of a uniformly charged plane, say the xy plane, with charge sigma coulombs per meter squared? First, I'll show the direct approach without Gauss's law. Then I'll show how Gauss's law handles the problem. In the first approach, we calculate the electric field at a point distance little r above a charged disk of radius big R. Then we'll let big R tend to infinity and derive the field induced by the whole plane. As usual, I'll integrate over little r prime, holding little r constant. From the geometry of our setup, we get that in cylindrical coordinates, r prime is s prime phi prime 0, and r is 0, 0, z. Sigma of r prime is just a constant, sigma. Next, our work is reduced from doing 3 integrals, one for each coordinate, to just one integral for the z-coordinate, since the symmetry of the charge implies that E of r points straight up. At this point, we're left with a nice calculus problem, an integral with no physics, just math. So you should pause and try your hand at it. Since the integrand is not a function of phi prime, that integral turns into a 2 pi. After pulling out some constants, we'll need to do a u substitution to get that denominator under control. Since u equals s prime squared plus z squared, the integral from 0 to big R becomes an integral from z squared to big R squared plus z squared. Here's something we can integrate directly. After evaluating at the limits of the integral, we get our not so pretty answer. E of r is 0, 0, 2 pi ke sigma z times 1 over z minus 1 over the square root of big R squared plus z squared. As promised, we send big R to infinity and get our answer for the electric field above a uniformly charged plane. 0, 0, 2 pi ke sigma. As always, it's a nice sanity check to make sure the units on the left and the right are equal, but I'll leave that to you. Alright, now here is the solution to the exact same problem using Gauss's law. We think of a box sitting symmetrically above and below the plane. Say the area of the top of the box is A. Then, since E points straight up when we're above the plane and straight down when we're below the plane, the integral over the box of E dA is 2 times A times the length of E. On the other hand, Gauss's law says that this integral equals the amount of charge enclosed in the box, times 4 pi ke. Rearranging the terms a little, and remembering that E points along the z-axis, we have our answer. E is 0, 0, 2 pi ke sigma. The same answer we got before. There are no tricks here. That's just the power of Gauss's law. That box we used is called a Gaussian surface. In this problem of a uniformly charged sphere, I've recommended a Gaussian surface in turquoise. Can you compute the electric field?